Okay, I think we're ready to roll here. Okay, so section 2.3 is all about continuity, and we've talked a bit about this in the past. Like in pre-calculus, we talked about when things are continuous or not continuous, and so I wanted to kind of revisit that a little bit with you guys here. Kind of the basic definition of continuity, I think the easiest way to kind of think about it is something is continuous at a point if you can trace it with your pencil and not have to lift up your pencil to go over it, that sort of a thing. So we're going to talk about kind of the difference between that idea, being continuous at a point, and then having a continuous function, because they are two different things. Okay, so basically it's this. You have to have a few things happening all at the same time. So if the limit as x approaches a of f of x is equal to f of a, then f of x is continuous at a. And that means, and I said there's a couple of things going on there. So in this limit right here, that means the left and the right-handed limits are the same. So they're both pointing to the same place. So as you go from the right and you go from the left, they're going to the same place. And not only that, the function is defined at that same exact spot as the same thing. Okay? So it's not a situation like this. Like if I had a function with like a hole in it like that. Okay? Do you see how that fits just the left part of this? That yes, the limit does exist there, but it does not equal f of a, right? Because the actual point right here is missing. Okay, so if that were like a, like let's say here's my x-axis down here, there's a. So for that one, the limit as x approaches a of f of x exists, but it's not equal to f of a. Okay, because the function's not defined there at a. So if I wanted to evaluate that function at a, I wouldn't get anything for it. So it's not continuous at that point. However, if that were filled in, then I would be continuous there. Okay, because now the limit as x approaches a does equal f of a. Okay, as I come from the left and the right, yep, those are coming to the same place, and not only that little hole's filled in. It exists. Okay, so I can do f of a and get an answer, and it's equal to what that limit is. Okay, so that's how we're going to check for continuity at a point. And there are some different ways that we can not have continuity. Okay, that's what we're going to kind of investigate here first is what are the different ways that we could lose continuity at a point? Because usually we have it. Usually it's this nice, smooth, connected, function, that sort of thing. We see that more often than not. So it's probably easier to look at, okay, what are all the ways that that doesn't happen, and how do we recognize that? So this is something that we talked about in pre-calc a bit. So these should look a little bit familiar. We got these are discontinuities. So this is a jump discontinuity is one way. And in that case, we can lose continuity if we got a function that's going along and then it suddenly stops and then like jumps up to another value and then keeps going. It would look something kind of like that. So Can you guys think back to when we talked about all like those 12 basic parent functions in pre-calc? There was one that had a whole slew of jump continuities all over it. Remember what that was called? Yeah. The step function, right. So a step function has points of discontinuity all over it because every step is a jump, a jump, a jump, a jump. So, yeah, that's kind of the most, I think, recognizable function that has jump discontinuities in it. There's the removable. That's another one. And removable is actually kind of what I was talking about up here with the A stuff. I used an example of that. So for that one, you've got just a hole. And sometimes it's just the hole like that. There's just one missing point. Okay? So there's like a point has been removed from the function. Other times you've got the hole, but then maybe the point is like up there or something. Okay? So if the point is included and it's just like floating somewhere else, that just means your domain is covered. You've got every single point still in your domain. It's just not continuous at that particular point where it takes it out and puts it somewhere else. But that's what those generally look like. Some other ones that you guys have seen, infinite. These are probably the most common. And where do we see infinite discontinuities, do you suppose? What are these things that pop up in functions that as we're going along, then, oh, now we're going to infinity, and we can't keep going? Asymptotes, right. So some kind of vertical asymptote is in the way. So maybe we're going along, and then, oh, yep, we're caught. We can't get past this asymptote, and then the other side, it continues on, maybe something like that. Okay. So those come about. And then there's another one that is really rare, but still exists, so it's worth talking about. And that's an oscillating discontinuity. And these are kind of challenging to draw, so bear with me. But basically what happens with these is you've got usually some kind of a sine or cosine function has had something funky happen to it where it's going to oscillate back and forth between two numbers, but that oscillation, as you approach a certain number, is going to get more and more and more and more, and then it just goes nuts. And it just oscillates so much that it can't get past where it's at. So it keeps going back and forth, tighter and tighter and tighter and tighter and tighter, and then it cuts out.